Alright. Let's pick up where we left off last time. We had a sequence alpha I of points of degrees bi and mu I was the average of the Galois orbits of these points. Let's measure, and we pick a subsequence that converges to mu. And we had di were the discriminants of the minimum polynomials of the alpha I, and we showed that mu was supported on S1 and mu assigned every point measures 0. Okay, so we're in the middle of computing the energy integral I of mu was this thing, and we defined the sort of I epsilon mu was a sort of slightly smoothed out version where this phi epsilon function, and I sort of messed it up last time, what the phi epsilon function is, I'm just going to draw it, into sort of 0 until epsilon, and then it becomes 1 at 2 epsilon, and then it's 1 for a while, until say 1 over epsilon, and then it becomes 0 again. So a slightly smoothed out version of log x minus y. Okay? And we showed, remember we had that the log for the discriminant was di times the log of the leading coefficient of the minimal polynomial of alpha I plus this average. And we showed this guy was little o of d sub I, which, from which it follows that if you look at this sum, and you normalize it, that if you look at the limit of this, or the lim sup of this, the limit of this, the limit, I guess, makes sense. The limit of this is greater than or equal to 0. Okay? Because this is little of this about. So this is what we sort of had going last time. Questions about this?
Sorry,
yes.
What's that log of sigma I? And this can't be different.
Oh, this is sigma doesn't equal sigma prime.
The line above.
Log of absolute value of d sub I.
Oh, okay.
Discriminant of alpha I. Yeah, no, that's interesting. Alright, so we want to make a limit argument now, so we're going to use the phi epsilon instead. So first of all, note that from here, what we get, sort of a fortiori, is that if we add this phi epsilon function well, what we're doing, we're sort of removing the very low contributions where sigma alpha I and sigma alpha prime are very, very small. And also, when the difference is very, very high with the contribution, but the difference is only very, very high very rarely, because we know the height of these guys tend to 0. Okay? And so because of that, sort of effectively this part, 1 over t sub I squared tends to 0, because the heights go to 0 by similar argument to last time. So essentially we're just taking away the sort of negative values when this log is of something very close to 0. So this guy, this limit is bigger than this limit. So this is also bigger than or equal to 0. Okay? And the advantage of this function is that it's bounded. It's uniformly bounded everywhere. You remove both the little values and the big value with this piece of epsilon function. And so, since this is bounded, above and below, and when mu I goes to epsilon, well, sort of at every point, integrating with respect to mu I is very close to integrating with respect to mu, and so you can conclude that if you take the, so if we rewrite this, sort of, what is this line over here? Both in our notation, it's I epsilon of mu sub I. And so we can conclude that I epsilon of mu is bigger than or equal to 0 for every epsilon, for any epsilon bigger than 0. And now, since mu assigns every point measure 0, because this is true, if you look at mu cross mu, which is what this integral is taken with respect to, and if you look at this of the diagonal, so the subset x equals y, this equals 0. Right, by sort of make it, whatever, integrate one point at a time. And so as a result, you can take the limit inside the integral, and so you get that I of mu is bigger than or equal to 0. Okay? So this part is a little confusing. This whole song and dance is just to sort of take a limit from here and conclude that I of mu is bigger than or equal to 0. So if you're sort of willing to accept that, then this is all sort of unnecessary. But this sort of song and dance about, well, take this log, first sort of smooth it out a bit so it's measure's not so big, and then make sure you can take the limit inside the integral. It sort of can get a little subtle. Alright, so at the end of the day, we showed the integral was bigger than or equal to 0. Okay, so we're about to go through another song and dance to conclude that mu is actually just the R measure now. So before we do that, let me just give the idea of the argument. What we want to do now is the following, is just to use, there's a potential theory argument for this, which I don't really know, because I don't really know potential theory. But one argument you can use is you can use Fourier theory. Now this is a bit subtle because mu is just some random measure. It's not an Elton function, and so using Fourier theory is not wholeheartedly justified at this point. But so we'll sort of do a little trick to make sure that it's fine. I'll explain how to do it at the end. But let's just pretend for a moment that everything we know from Fourier theory is fine in this context. So if we write mu of x is f of x dx. So pretend that somehow we know that mu is an absolutely continuous measure, for example. Then we can write mu of x in this form. So write this, and then let's sort of mu hat of n be the integral over S1 over the unit circle, so of f of x, x to the n, dx, sort of normalized. Sorry, if we do it like this, then it's just this. So we're integrating it against the nth power of x, which is a character. See, if you want to think in terms of theta, then this is, if you want to write this as f of theta, f of e to the I theta, d theta over 2 pi, then this is just the integral f of theta, e to the I n theta, d theta over 2 pi, the angle. And this is if you think of just a complex variable, which this actually represents. Okay? Okay, so now I of mu is the integral of log x minus y, f of x, f of y, dx dy over S1 cross S1. And now, if you look at the Fourier coefficient of log x minus y, the sort of the integral of log 1 minus x against x to the n is 1 over n, as x goes over the unit circle. And so if you work out this double integral by Fourier theory, this is the sum over n. If you sort of convolve this, maybe I'll do it in the, maybe I'll do it in full. I'm going to do it in full up here. Let's make the steps. So we're going to change variables. So on the unit circle, so I can replace this by 1 minus 1 over x. I'm going to change variables to do f of x. Well, actually we're going to write this out in full. So this is the sum over integers n m of mu hat n, mu hat m, x to the n, y to the m, dx dy. Now everything dies unless m is equal to minus m, because this is invariant under Torr's sort of x equals y. So what you get is a sum over n of mu hat of n, mu hat of minus n, divided by n. There's a minus over here, sorry. And this is the conjugate of this, and so what you get is minus the sum over n, mu hat of n norm squared, divided by n. Sum over n not equal to 0. This is if n is bigger than 0. If n equals 0, you get 0. Okay? So if you were allowed to Fourier expand mu, you would get this sum. And so this is less than or equal to 0 with equality if mu had a value 0 for all n bigger than 0, or for all n not equal to 0, i.e. if mu is just the Haar measure on S1. Just wanted to show. Okay? This makes sense to everybody? So, before I explain how to do this sort of for real, not cheating Fourier theory, let me just mention that we sort of get a little lucky in this proof, I think, in my opinion, even though it's generalizable, but sort of not as lucky as it might look at first. So, it's sort of, the one bit of luck we do get is that this function happens to be minimized when mu is equal to Haar measure. I don't personally know for great reason why this sort of had to happen ahead of time. Given that it does happen, the bilinear form we got over here had to be negative definite. Because if there was even a single sort of positive coefficient, we could just tweak mu a little by increasing that mu hat, you would still get a positive measure. Because if you take the function 1, you perturb it a bit, it's still positive. And then you'd be able to sort of make this bigger than 0. And so, given that this is minimized by sort of Haar measure on S1, this analysis sort of has to work out in a rather straightforward fashion. Okay? Questions about the idea? Yes, sir.
Yeah, where is it cheating there when it's just when you start?
Well, it's cheating because you can't do this. Yeah. So I don't know. This argument is in. There's actually. I should mention this anyways. Probably. There's this book by Bombieri and Gubler. Called Heights in Diophantine Geometry. And section 4 of this book has most of what we've been doing so far, and it has this argument. And they sort of say that this is fine to do, but they're rather sloppy. So I don't think it is, without saying more. Anyways, yeah, I don't know if Fourier theory applies for functions that are for just sort of regular measures and stuff. You certainly can't expand like this. So, as far as I know, this is slightly cheating and say a few words to justify it. But maybe it's not if you know enough analysis. Okay, but let me explain how to not cheat. And the original paper of Bilou is going to work around this in the same way I'm going to explain now. So he also thought it was cheating. Okay, so to not cheat. Do the following stuff. So step 1 is you notice that if rho is bigger than 1, then for any function s and s1, for any element x on the unit circle, the log of 1 minus x is less the log of 1 minus rho x, just because this quantity is less than this quantity, and log is an increasing function. Okay? This is some geometry, which I'm going to leave you guys to do by yourselves. But this is true. So therefore, we know that the integral of log x minus rho y mu x mu y is greater than 0. As we know, it's greater than or equal to 0 if you take rho equals 1, then if you take rho equals slightly bigger than 1, this makes this bigger everywhere. U is a measure, and so you get something which is slightly bigger than 0. So now what you do is, well, this guy is now a totally bounded function on the unit circle. And so now you approximate mu by a different measure mu prime, which is given by a differentiable smooth measure in S1, which you can do because all measures sort of at the L infinity norm, as we showed before, these guys are dense to the space of all measures. And because this guy is bounded, if you approximate this guy in the L infinity norm, you can approximate this integral as well as you want as well. So such that, first of all, if you look at this integral, it's still bigger than 0, which you can do. And mu prime hat of 1 is equal to mu hat of 1. So if you integrate x with respect to both of these, you get the same number. Okay? Both of these things you can do. Because log x minus rho y is bounded everywhere. Let's see. So now, use Fourier theory. On the prime, which now you can totally do because it's a smooth function, so it's certainly given by something in L2, everything's totally fine. Now if you look at log of 1 of x minus rho y, well, this is log rho plus log 1 minus rho inverse x over y. So this is log rho minus the sum over n of x to the n divided by n with a rho to the minus n out front. And so by the same Fourier theory argument, you conclude, if you run through, that log rho minus sum n, rho to the minus n, this squared is bigger than 0. Now you have sort of an n equals 0 contribution, because n doesn't equal 0. This is divided by n still. And so now rearranging, you get mu prime hat of 1 in particular is less than log rho times rho to the minus n. But this is also mu hat of 1. And this tends to 0 as you make rho closer and closer to 1. And this is, sorry, absolute values here. I want to say. And so you can show that mu hat of 1 is 0. So likewise, you can, by making this one different numbers, you can show mu hat of any number is 0. Okay. This is how Bilu gets around this sort of thing. So this is like a technicality, I just want to emphasize that, but technicality which sometimes matters and sometimes doesn't, so it's just to sort of know how to deal with it. Alright, let's give it the proof. Questions? Comments? Okay. So what are we doing? Well, we've now got the second distribution theorem that says that these points of small height, if you look at the measure they give, they converge to our measure. And so we can use this now to give an upgraded version of Lang's theorem, known as Zhang's theorem, which Zhang proved using a different method, which we'll explain in a bit, maybe, which allows you to go from reducibility to just points of arbitrary height. So how do you phrase this theorem? Well, you say it in the following way. So actually, I gotta give one definition before I give the theorem, sorry. So we define heights of algebraic numbers, but not points in a to the n. So if you look at just any algebraic point, you just define the height of the n tuple to be the max of the heights of the coordinates. Okay, this is how we talk about heights inside affine space. Definition. Okay, so Zhang says the following thing. So take x and c star to the n to be a closed subvariety. And now let's remove all the torsion cosets of x. We sort of know already from Lang's theorem that those form a closed subvariety. So let x star and x be the union of the maximal, or as I say, if we remove this word, of the maximal torsion cosets inside x. Okay, so in Lang's theorem we show there's finitely many maximal torsion cosets, so we're actually talking about a subvariety now in x. So a priori that's not clear. So then there exists some delta bigger than 0 such that if you look at the height of any, now we're going to stick to q bar points because the height doesn't make sense for non-q bar points. But if you look at the height of any point in x that's not an x star, well, we know that heights here are positive, but for the height to be 0, you're according to the roots of unity, so it's certainly inside a torsion coset. But in fact, there's a uniform lower bound from all of these guys. So, sorry, I'm taking the height of the set, so I'm saying the height of any value here is inside the interval delta infinity. So, at least delta. Okay.
Which Jang is this? Is Shogu Jang?
This is Shogu Jang, yes. That's right. Okay, so this basically follows through the same kind of proof that we had for reducibility, with sort of a few minor tweaks. So let's go through it. So first of all, same as last time, you can assume that x is defined over q bar by intersecting it without its conjugates, getting something over q bar. Intersecting it without over q bar is the first step, and then likewise by taking the union of x and its finitely many conjugate, you can assume that x is defined over q. The statement doesn't really change if you replace x with the union of finitely many conjugates. And then also, by induction on n, you can assume that x is not contained in a torsion coset. Is not contained in a torsion coset. Because if it is, well, that just looks like c star to the n minus 1, and then you can just apply induction. Okay. So I'm not going to go through these again. It's sort of the same as it was for reducibility. So we're going to use the same equidistribution argument. So we just need a small lemma. So that if you take any non-trivial algebraic character from c star to the n to c star, then the height, there exists some positive constant, a chi, such that the height of chi of some number is bounded above by a chi times the height of that number. So essentially, if you have a sequence of points here with small height, then if you take the image here, they have small height as well. Okay. The proof is really simple, so we know what the characters are. The characters are all of the forms z1 to the a1, z2 to the a2, times zn to the an. For the a is just some set of integers. A is just, and so then by the product formula, we get that. So you can take a chi to be the sum of the absolute values of the a sub i's, because you have that sub-additivity on the multiplication. Okay? Okay, so now let's prove Zhang's theorem. So assume the theorem is false. So the proof is I'm about to give it is like extremely ineffective, right? In fact, the proof of the distribution theorem we gave was extremely ineffective as well. We sort of passed a subsequence, we picked some measure, we got some contradiction. It is effectivizable, but we're going to see other easier effective proofs. So I'm not going to make this one effective. So in principle, you can sort of make all of this effective. Essentially, by sort of the way to make sort of the previous argument effective is instead of first passing some subsequence, you just take some test function and stick with it sort of the whole way. Okay, but the Tsimerman theorem is false. So then you have a sequence Z1, Zn, points in X, which aren't in this X star, with the height of these guys going to 0. No lower bound sort of phi, so you can find a sequence which eventually goes small as 1. But you also don't have any of these guys with height actually 0, right? Because that would mean they're unities, they're inside X star. Okay, so now we're going to show that these guys become equidistributed. So claim. So for any non-trivial algebraic character chi, and any element R in C star for big enough I, chi of Zi is not equal to R. So if you take any character of the sequence, it doesn't stay constant. It eventually goes outside of any given integer. This is setting up the same distribution argument as before. Okay, so there's two cases in the proof. So, case 1 is that the height of R is 0. So R is a root of unity. Jordan point inside the C star. Those are the only numbers with height 0. Only numbers with height 0. So now, take X prime, be the intersection of X with a set of points where chi of Z is equal to R. Chi of Z from K. So now, this is just like C star to the n minus 1. We can apply induction to X prime. So by induction on n, we know that the height of X prime minus X prime star X prime is bounded from below. Okay? And X prime star is inside X star, because anything which is a torsion coset inside X prime is certainly going to be inside X. Torsion coset inside X prime, and the height of the Z's go to 0. So for I bigger than big enough, Zi is not an X prime. Okay? Okay, this is the case where R is root of unity. Then we have one more case. Unity. Then second case is that the height of R is bigger than 0. Height of R is bigger. Then by the lemma we just had, we have that the height of these z's is at least a chi inverse a times the height of r, which is bigger than 0. Right? But the height of this d sub I is the height of height of z sub I. But we know that these heights tend to 0, and so for big enough I, you can't be inside here. Okay, that's both cases. Okay, so then chi of z sub I is a sequence of algebraic integers with heights going to 0 and degrees tending to infinity and non-constant. So, and 0 and by picking a subsequence, we can assume the chi of z sub I are distinct. And so by Belou's theorem, which we just proved, if you look at the Galois orbits of these guys, so this is equidistributed with respect to the Haar measure on this one. Respect to the Haar measure on this one. Okay, but what is the set? Well, this set is exactly chi of the Galois orbit of Zi. So this means if we take any limit measure of these guys, it'll have chi Fourier coefficient 0. These are all non-trivial chi. And so therefore, as before, and so just like with rotativity, this is supported. So if you look at the set of these measures, this converges to Haar measure on the product of the unit circles. And so therefore, X must contain this ginormous set, the ginormous algebraic variety, which contains all of these points, is X being all of C star Vn. It is X being, and the statement is surely true for C star Vn, so I wouldn't do this. Okay? So modulo a couple sort of simple details, you lose the Belou's theorem pretty immediately by taking the chi Fourier coefficients again, because we have this very useful fact that if your height is going to 0, then if you take chi, your heights are still going to 0. So reduce the body number. Okay, so take chi. Alright, I'm over time. Sorry again for starting late today. So next time we'll talk a bit about sort of higher up versions of length conjecture and higher up versions of length proofs. Thanks.